This is a pre-recording for Master of Engineering, Industrial Automation, and this is week 11. And in this pre-recording, we're going to look at the following topics: introduction into safety PLCs, the architecture of safety PLCs, the characteristics of safety PLCs, hardware and software characteristics of these safety PLCs, redundant architectures for high reliability, and application software for safety PLCs. Now, in this slide, we've got a picture on the left-hand side of a typical PLC, which is manufactured by Allen Bradley, compared to the PLC on the right-hand side, which is safety PLC, which immediately shows additional modules added to the PLC and also indicated in red so that you can see it's a safety PLC. Now, in 1998, the first part of a 7-part international standard was published to define the requirements for programmable electronic systems used in safety-related parts of control systems. This standard was known as IEC 61508, Functional Safety of Electrical, Electronic, Programmable Electronic Safety-Related Systems. And this 7-part standard is driving the direction for future safety PLC developments. Now, over the past several years, manufacturers have developed specially adapted PLCs for high safety integrity applications. Now, in a safety PLC, there can be 2 or 3 microprocessors that perform exactly the same logic, check against each other, and only give outputs if there's agreement between them. So these are commonly required in the following categories of control applications: high availability basic control systems for machines and plants, where downtime cost and consequences are severe; safety critical or safety related applications for protecting machines and people against dangerous such situations. And there are 3 fundamental differences between the safety PLC and the standard PLC in terms of architecture, inputs, and outputs. So if we start with architecture and looking at the basic design differences, now a normal or general PLC has got 1 microprocessor which executes the program, a flash area which stores the program, RAM for making calculations, ports for communications, and input, output to detect and control the machine. Now, in contrast to that, a safety PLC has redundant microprocessors, redundant flash and RAM that are continuously monitored by a watchdog circuit and a synchronous detection circuit. Now, if we compare the normal PLC, which is in the picture that you see on top, so there's the 1 microprocessor. We have the address, data, and control lines, and with this we also then have there's the flash, the RAM, the ports, and the input-output module. Compared to the bottom, where we have the safety PLC, where we have redundant microprocessors. Instead of 1, we have 1 on the top, 1 at the bottom, with a sync circuit in between. And then similar, we have address, data, and control lines. But different now, we've got our watchdog or our compare circuit, which will then continuously, so this flash and RAM is continuously monitored by the watchdog circuit and a synchronous detection circuit, as I have pointed out. So say there's the additional flash and RAM as well. Then if we look at the differences in terms of inputs, your standard PLC inputs provide no internal means for testing the functionality of the input circuit. And again, by contrast to that, your safety PLC have an internal output circuit associated with each input for the purpose of exercising the input circuitry. So your inputs are driven both high and low for very short cycles during the runtime, just to verify their functionality. Now again, on the picture on top is just the general PLC, where we have there's the different inputs, and we have the microprocessor again with the ports and the different address data and control buses. So the internal output circuit associated with each input. So there's input, and there you can see there's the test signal going back from each input, going to the test control circuit. And again on the left hand side you see we've got more than one microprocessor, we've got our sense circuit, and we've got our watchdog and compare functionality over there. So the inputs are driven both high and low for that very short cycles, getting a runtime, and that's to verify their functionality. Then on the output side, just again the general PLC has got one output switching device, whereas a safety PLC, the digital output logic circuit contains a test point after each of the two safety switches located behind the output driver, and a third test point downstream. So each of those two safety switches is controlled by a unique processor, and if a failure is detected at either of the two safety switches due to switch or microprocessor failure, or at a test point downstream from the output driver, the operating system of a safety PLC will automatically acknowledge a system failure. And at that time, your safety PLC will default to a known state on its own. So that will facilitate orderly equipment shutdown. So there again on top is the general PLC with the microprocessor and the output circuit. While at the bottom, we again have duplicate more than one microprocessor. We've got our watchdog compare block, and then we've got all these monitors. So the test point after each two safety switches, and it's controlled by a unique microprocessor to make sure that we can monitor that, and then, as we've mentioned, we can at the end of the day, if there's a problem, facilitate the orderly equipment shutdown. Now what we also need to consider is safety relay or safety related PLC. Now a machine and robot builders often need safety rated monitoring and control, which can be accomplished with safety rated relays or PLCs. So many applications could use either a safety relay or PLC, but the choice will depend on the main considerations: the complexity, the flexibility, the availability, and the footprint. So your safety applications become complex when more than about 3 inputs must be monitored. So that's the guideline: more than 3 inputs to be monitored and controlled, or when the communication over digital network is required. So that's where your safety applications become complex. Safety relays are hardwired to perform simple diagnostics and logic, and it works well when the amount of safety points in your application are small in number and also simple in functionality. So they're well suited for standalone machine safety applications that have a maximum of 2 to 3 safety devices or functions. For example, a single cell robot control for e-stop and door monitoring. But any application with more than 3, so that's the guideline again, more than 3 safety devices or functions, or a requirement for safety networking, can best be served by moving over then to a safety PLC. Now a simple gravity-fed roller conveyor that feeds upstream from its chute with a normally closed feeder door. So there is walking access to the conveyor on both sides for about 6 feet to allow for unloading and stacking manually. Now conventionally, light curtains on both sides span the access points. So in this case, a standard safety relay tied into the existing e-stop circuit is sufficient. Why? Because the light curtains only need to trip the emergency stop and not allow the feed chute to open when somebody is present inside this access point. Now, if we have a powered feed conveyor which is used to drive empty pallet stacks into a robotic arm bay, so the robot picks up a pallet, turns it 90 degrees to place it on a loading conveyor. It's then stacked and driven out of the bay on another powered roller. So on each conveyor entering and exiting the bay, a set of conventional light curtains are used. And these light curtains must then be able to shut the system down if a person or foreign object enters the bay. And it must be done in a safe and orderly manner due to the possibility of the robotic arm holding a pallet in mid-cycle. So this is then a case where a safety PLC would be very useful, because your system cannot be simply shut down instantaneously. It must retain grasp of the pallet, but it must stop movement of rollers and robotic arm instantly. So you can see that it becomes more complex than the first example. So when the feed pallets enter into the bay on the conveyor, it must break the light curtain plane in order to enter and exit. The safety PLC, with the help of the position sensors on the conveyors, can turn off the light curtains on the delay for the pallets to enter without tripping the safety system. So with these two simple examples, it's easy to see the advantages and disadvantages depending on the system needs. So you can see if it becomes more complex, we need a safety PLC. So most systems could be designed using either multiple standard PLCs or many relays and safety interlocks. Now, even though they cost about 50% or more than a standard PLC, the extra cost of the specialized software and the time added engineering would make it a cost prohibited to not use a safety PLC. Having an underpowered or incorrect device can be a very expensive mistake, just as an overpowered high-priced system that will not be used to its full potential. Okay, moving over to the architectures of safety PLCs. Now, let's first look at safety integrity level, SIL. Now, this is the assumption to what an extent can a process be expected to perform safely, and in the event of failure, to what an extent can the process be expected to fail safely. So it's performed safely as well as fail safely, and these questions are answered through the assignment of a target safety integrity level, SIL. Now, so it is incorrect to call a particular safety system as SIL1 or SIL2. Either it is correct to say a particular safety system is suitable for use in SIL1 or 2 environment. And there are 4 levels which have 3 important properties. Applicability to the overall safety function. The higher the SIL, the stricter are the requirements. And applicability to technical and non-technical requirements. Now here you can see a table showing the SIL safety integrity level according to the specification that we've mentioned when we started this pre-recording. Second column shows us the availability, and the third is the probability of failure on demand, and then lastly we've got the risk reduction factor. Now you can see, going from basic process control system, we start with 0. Then 1 is slight impact to property and protection of production. Then protection of production and property, partial damage to employee. Then we get protection of employees and community. And then we've got catastrophic impact for community. So you can see the availability is very high as we go up. What goes down is the probability of failure on demand. So that the lowest level, of that the highest level, and then the risk reduction factor. So that shows us the different levels from 1 to 4 in terms of SIL levels. Now, if you look at the consequence range, then when sitting at level 4, individual, multiple critical injuries or fatalities, public, potential or critical injuries or fatalities, environment, the release of unconfined with high environmental impact, and then that reduces as we go down, getting to 1, individual injuries require first aid, public, smell, noise, disturbance, no direct impact, environment, release of unconfined with located impact. And in terms of property, if you look at the loss between US dollars 100K to US 1 million, and here you can see the loss is higher than 100 million, which is a big difference if we're going from level 1 to level 4. So this is the SIL selection, which is based on risk posed by the hazard. Now, the safety standards have set down guidelines for fault tolerance structures in PLCs that are to be safety integrity level rated. So SIL-1 systems can operate with a single channel PLC provided it has good fail-safe characteristics and has got an internal self-checking diagnostics to detect at least 60% of all known failure possible. And the diagnostics must be arranged for a safe shutdown of the plant if failure is detected. SIL-2 systems generally require a dual-channel PLC design with 1002 or 1002D or 2003 architecture. So if your diagnostics and safe failure behavior can be used to ensure that more than 90% of all failures result in a safe shutdown of the plant, then it's permitted to use a single channel PLC. Getting to SIL-3 systems require dual channel design systems as a minimum and require 1003 designs if safe failure fractions are below 90%. Now, getting back to the safety integrity levels, it's the measure of the degree of confidence that can be given to the ability of your safety system to provide risk reduction. So you can see the risk reduction factor goes up as we go from 1 to 4. Probability of failure then must come down as we go up to 4. So in functional safety systems, the safety integrity is defined by safety integrity levels, or SILs, and there's 4 levels of safety integrity that are recognized, and the risk reduction capabilities are defined by these values. So again, looking at SIL 1, 2, and 3, risk reduction between 10 and 100, which then goes up to 100 to 1000, which goes up to 1000 to 10,000, getting to SIL 3. Then more than 95% of the process safety systems do not need more than this, which is SIL 1 level. Now, typically, smaller than 5% of the process safety systems need SIL 2, which means moderate engineering effort, usually feasible for SIL 2. Then getting to SIL 3, substantial engineering effort, usually feasible, and you see typically 1% of your process safety system needs this. So it's not all the systems that need this, but it is specific safety systems that do need the higher SIL rating. And then as expected, as you go up in terms of SIL, the cost will also go up. Looking at the logic solvers, the input devices, the actuators, the engineering and the maintenance, all of those components in terms of cost per function increases as we move from SIL 1 to SIL 3. So it becomes more expensive, but that's what you need for safety. Now, if you look at fault tolerance definitions, starting with fault, what is a fault? Fault is a malfunction or deviation from the expected behavior. Tolerance has the capacity for enduring, and putting the words together, we get to fault tolerance, which then refers to a system's ability to deal with malfunctions. Now, the general approach to building fault-tolerant systems is redundancy. So we ask the question, how do we achieve fault tolerance? So firstly, information redundancy seeks to provide fault tolerance through replicating or coding the data. That's more relevant to the data, the information. Time redundancy achieves fault tolerance by performing an operation several times. Physical redundancy deals with devices, not data. So we add extra equipment to enable the system to tolerate the loss of some of the failed equipment. Redundancy is the inclusion of extra components in addition to those being used for the critical functionality to increase the reliability and the availability of the system. And redundancy can be added in the form of hardware, for example, the dual-core lock steps, in the form of software, in the form of information, and time redundancy. So in general, redundancy works on the MOON concept. Now, what's the conventions for describing fault-tolerant structures, M out of N? Now, the notation, as we already mentioned, MOON means that M channels of a subsystem are required to act or vote in agreement before the action is implemented. And the total number of channels provided in the subsystem is N. So the voting structure is then described as M out of N. So for example, 2003 means any 2 channels out of 3 must agree before the action is taken. So any 2 channels, so in total we have 3, any 2 of that 3 must agree before action is taken. So your M out of N systems contain N identical components, and it works on the principle that if at least M out of the N components are functioning correctly, the system is error-free. Now, example here is the triple modular redundancy, which is actually a 2003 system. Now, if at least 2 components of the majority out of 3 are working correctly, then the system is considered to be functional. So there you can see this component 1, 2, and 3, and 2 out of the 3 must be working correctly, and then the system will be considered functional. Now, MOON systems are used in hardware as well as software. So in hardware, critical components are replicated on the basis of the majority voting. The decision is then taken. Now, if you start looking at the 1000 architecture, now this represents a minimum system. So no fault tolerance is provided by the system. No failure mode protection is provided. Your electronic circuits can fail safely, which means output de-energized, open circuit, or it can fail dangerously. So that means output frozen or energized, short circuit. So there's the output circuit. So if it fails open circuit, then it's fine because there's no power going to the actuator. So that's safe. But if it fails short circuit, then it means we will have continuous power to the actuator with no means of disconnecting that. Now, since the effects of your online diagnostics should be modeled, 4 failure categories can be included: dangerous, detected, dangerous, undetected, safe detected, and safe undetected. So you can see here, looking at the PFD fault tree for the 1001 architecture, unit files dangerously detected or unit files dangerously undetected. So it depends if it's short circuit or open circuit, but that's how it can fail. So, but it can be safe or it can be unsafe. Now, the voting principle of 1001 involves a single channel system, and it's normally designed for a low-level safety applications. Immediately results in the loss of the safety function or the process closure. So you've got your safety transmitter, your safety PLCs, and that's driving valve control circuit at the end of the day. Now the 100D architecture, so we've got a single controller channel with diagnostics capability and a second diagnostic channel wired in series to utilize the diagnostic signal to de-energize the output. So on the left hand side we've got a previous one, and now we've added diagnostic circuits, the D that you see added to the 101 architecture. So it differs from the 101 only in that the switch is wired in series with the output to de-energize the output. So you can see there it's wired in series. So it's an enhancement that's used for safety applications, and the diagnostics allow a detected dangerous failure to be converted into a safe failure. So now it can fail at the end of the day, short circuit. So we've got something in parallel that we can use to change that to a safe failure, which was now previously dangerous failure. So additional failure rates must be included in your quantitative analysis to account for that extra diagnostic channel which is now being added. Then 1002 architecture, so two controllers can be wired to minimize the effect of dangerous failures, and for de-energize the trip system, a series connection of the two output circuits requires that both controllers fail in a dangerous manner for the system to fail dangerously. So both of these must now fail short circuit for dangerously. So it's two independent main processes with their own independent input-output, and it offers low probability of failure on demand, but it increases the probability of a fail-safe failure. Now the false trip rate is increased in order to improve the ability of the system to shut down the process. So there's the diagrams for 1002 and 2002. So 1002 fault tolerance is 1. So at least one of the two should be operational. And 2002 fault tolerance 0. So both of those must be operational, and not just the one. Now 1002 architecture is similar to 20D architecture, except that additional control lines are added to allow one unit to de-energize the other unit. So there's 1002D architecture. So you see that we've got control lines that can now de-energize the other one. So this architecture is defined as normally operating with all four switches closed, and the primary difference in 2002D versus the 1002D is when there's a dangerous undetected failure in one unit, because that added control lines and readback diagnostics, the operating unit can be de-energized, the failed unit, and it provides 1002 type functionality in the system. So that's the advantage of the 2002. So there's 1002 diagnostics. So again, you've got the two channels, but now we've got that diagnostics that are shown to you in the previous slides. And 1002D also added diagnostics. So that's improving the safety of the system by adding the diagnostics. So the voting principle 1002 was developed to improve the performance of your safety integrity of your safety system based on 1001. So if a failure occurs in a channel, the other one is still capable of developing a safety function. So but this concept does not improve the rate of false trips. It can, even worse, it can increase the probability of false trips, where there's not really a fault condition. Now the duplication of the channels is significantly reduce the probability of a false trip, because both channels have to fail in order the system is placed under shutdown. On the other side, the system has got the disadvantage that your probability of failure on demand is twice higher than with a single channel. Then getting back to the 2003 architecture, that's designed to tolerate both safe and dangerous failures. So 2 units out of 3 are required for the system to operate. So that architecture provides both safety and high availability. So 2 outputs of each controller unit are required for each output channel, and the 2 outputs from the 3 controllers are wired in the voting circuit, which determines the actual output. So your output will equal the majority. So when 2 sets of outputs conduct, the load is energized. When 2 sets of outputs are off, the load is de-energized. And this is for showing you the 2003 architecture on the left-hand side. Now, a single fault can degrade models of 2003 architecture. So if we have open circuit failure, so those 2 open circuit failure, the system degrades to 1002 because only one channel will then operate correctly. Or where you have short circuit failure, then that grades to a 2002 system. So there's the 2003. 2003 fault tolerance is 1. And lost 1 system, and so if it becomes equivalent to 2002 if one channel has a dangerous undetected failure, because then you only have those 2 operational. This one is not operational at all. So there's 2003 again. So in the voting there are 3 channels, 2 requiring being okay in order to operate and to comply with safety functions. And the voting principle is better applied when there's a complete physical separation of the microprocessors. But that, however, requires that they are located in 3 different modules. So there's the 203 voting now in 3 different modules. Now getting to the characteristics of your safety PLCs. So your answer to the problem of undetected faults in PLCs lies in the concept of fault coverage through diagnostics and voting circuits in the use of redundant fault tolerant systems. So the answer to the problem of hidden defects in software is high quality embedded software with internal fault checking and recovery procedures combined with strictly defined and constrained user programming facilities. So what is a safety PLC? So the fundamental difference with a general purpose PLC is summed up in one word: diagnostics, as we showed you in all the slides up to now. So your safety PLC incorporates many diagnostic functions to detect any possible internal fault in the hardware or firmware, so that if you have a failure in the PLC, it does not cause any unsafe situation. So this, in essence, we will explain it a little bit more, but it also meets the design standard of the so-called Safety Instrumented Systems, abbreviated as SIS, which provides international standard IEC 61508 and others. Now let's see with an example what's diagnosis. The first figure what we have here shows a simple diagram of a digital output of a general purpose PLC. So we have a general purpose PLC and we have one output. Now if this output transistor is short circuited as indicated in red, then we have a dangerous failure and the valve that we're driving does not close when ordered by the CPU, because we cannot control the signal to the valve anymore. So what improvements introduce a safety PLC? Now for detecting the short circuit, it uses a diagnostic routine by means of micropulses. So there you see the micropulses and monitoring output status. So it can at least give an alarm in case of the switch now failed as a short circuit. And to further act on the output in case of failure, it uses a second transistor in series, which you can now see in the picture, with an interlock with the monitoring circuit called watchdog. So there you can see the watchdog, which compares the status of both output transistors. So there's your indicator of your micropulses, and there's the, in dotted lines, the monitoring of the output status of both of these switches. So in this way we get a safe output circuit, fail-safe, fault-tolerant from the point of view of safety. To get also availability, redundant architectures are used. In this example, what now we've done is we've duplicated the two. So there's our redundant system, paralleling the two circuits and both of them giving the same output. So now we've made it a safe output circuit, but we also added redundancy to the circuit now. So there are many diagnostic functions in a safety PLC, both the CPU and memory as inputs, outputs, and communications that then logically carries an additional cost. And then it's important to note that the design of a safety system must consider the entire SIS, the PLC, the field devices, electrical supplies, control cabinet design, software, etc. And some of the designs are very focused on one part, neglecting the others, and obtaining at the end a solution that's got weaknesses that must be correct. Now, statistically, there are more failures in sensors and actuators than actually in PLCs. Finally, your international standards make a classification of the applications according to its risk level. We already looked at SIL 1, 2, and 3, 4, and that's been part of the risk analysis to be performed by the SIS designer. So most of your safety systems falls within SIL 2 and 3, as we've pointed out when we looked at the percentages. Now, in summary, your fundamental differences of a safety PLC respect to general purpose are: 1, it meets the design standards of the safety systems, such as IEC 61508. It is certified by competent organizations, incorporates self-diagnostic routines of all hardware and software, so it will detect any dangerous internal fault, and if it occurs, it acts leading the machine or process to a safe situation. Now, the cost of safety PLCs is higher on the initial investment, the CAPEX, but certainly lower on the total life cycle, the OPEX. Now, getting into the more detail of the hardware and software characteristics of a safety PLC. Now, hardware characteristics, your automatic diagnostics continuously check the PLC system function at short intervals with the fault-tolerant time of the process. High diagnostic coverage means that at least 99% of all hardware faults will be detected and notified for attention and repair. So it provides a predictable and safe response to all failures of hardware, power supplies, and system software. And redundant hardware options are available to provide safe operation even if one channel has failed. Now, if you look at hardware characteristics, your fault injection testing of the complete design is performed to ensure safe failure response to all known faults. So input-output subsystems continuously check all signal channels. Your input-output bus communications are self-checking. Faults result in safe isolation of affected input-output groups, and we have high security on any reading and writing via digital communications port. Output monitoring, or readback, is a technique that uses an input channel to measure an output channel's value and compare it to the value demanded by the system logic. And this diagnostics can determine if the output has failed on or failed off. So your ladder logic must be written to ensure that each output is compared with its corresponding diagnostics input channel, and appropriate diagnostics are then generated. Now, here's some examples of output monitoring. So your safety PLC incorporate output monitoring into the input-output module hardware using special circuitry and onboard microprocessor to generate the diagnostics. So on the left-hand side, again, we've got output monitoring typically implemented in a general PLC. So you can see we have our output module, and then typical for 1 or 8 modules. And then additional to that, as you can see on the right hand side, we've got output feedback and output command. We've got the output switch monitor and the output protection circuit and solid state switch. And this is the block diagram and the difference between the general and the safety PLC output module that has got built-in output monitoring. Now this eliminates the wiring and programming required by the general purpose PLCs. It also relieves the application controller from the burden of generating these diagnostics. So this output monitoring provides valuable diagnostic information. However, it can do nothing more than enunciate the problem on its own. So in order to convert this potentially dangerous failures into a safe failure, an additional technique must be applied in addition to the output monitoring, and that we call guarded outputs. So series wire trip relays would be incorporated to protect the monitored outputs. So the output to the trip relay is programmed to de-energize if any of the output is protecting the reports a dangerous fault. So this provides a secondary means of de-energizing an output if for some reason the output fails to turn off when commanded. So additionally, a contact of the trip relay should be monitored to ensure that it is functioning properly. So there's the trip relay, and we need to monitor one of these contacts to make sure. And it must be manually reset before it can be re-energized. And it can be accomplished by just wiring a reset button to the input circuit or via engineer's console. So the typical addition of a trip relay to a general purpose PLC output. Now again, going to the safety PLCs, it incorporate protected or guarded outputs. So previously we just had the dotted lines. So there's additional functionality which is now added. So the relay is also monitored for proper function, and the diagnostics generated by the faulted output or relay must then be manually cleared before the relay can be re-energized. Then we also have processor protection, where your watchdog timer circuits are employed to ensure that the output fails safe upon detection of a processor failure. So your typical implementation with your general purpose PLC is to configure 1 or 2 outputs to continually generate square wave outputs. So your watchdog timer will trip if these outputs fail to change state within the timer specified preset, and that causes the trip relay to de-energize. So there's the watchdog timer circuit. Again, this is now a general purpose PLC application. So at least 1 watchdog timer monitoring every CPU in the system. 2 watchdog timers are required to detect watchdog timer failure as well. Getting back to the safety PLC, right on top there you see we've now added the watchdog circuits as well. So your safety PLC employ watchdog timers, and your watchdog timers are integral to the modules and usually implemented redundantly. And that is so that every CPU circuit is monitored by 2 watchdog timers, and the timers also monitor each other to detect any watchdog timer failures. So if either watchdog trips, the diagnostic cut-off relay is then de-energized. So there's your diagnostic cut-off relay. Then also power monitors. So your quality of the output signal is only as good as the power used to drive them. So to ensure the outputs are not turned on when the power supply is out of tolerance, we also now add the power monitor. So again, what we have is the signal conditioner or the trip alarm that will detect if the power supply is under range or over range. You can see there's a high and a low level trip. And to protect the output from damage, possible dropout or oscillation during brownout conditions, your PLC must be programmed to de-energize the trip relay if the output of the supply goes out of range. Now again, like the trip alarm, the power monitor circuit detects if the power supply goes over or under range. So there's the additional power monitor now. And it can also then detect if the main fuse is blown. So that's where we added onto the safety PLC. Now getting to the software characteristics. So your software quality assurance methods are deployed throughout the development and testing of your operating systems. And your software development takes place under the safety life cycle as specified in IEC 61508 Part 3. So your software design and testing is fully documented so that your third-party inspectors can understand and analyze the program operations. Special techniques that we have to ensure software reliability is program flow control. This is to ensure your essential functions execute in the correct sequence. We've got data verification stores all the critical data redundantly in memory and checks validity of before it's used. Operating systems and your user application software tools are approved for safety by a third-party approval bodies, and operating system and programming package supplied by the same vendor as the hardware. Now the software and hardware integration is tested by these approval bodies, and we've got extensive analysis and testing, carefully examines your operating systems, and you've got application software that uses limited variable languages, and all application software is updated transparently to the redundant channels. Looking at redundant architectures for high reliability. So what's the disadvantage of a single channel safety PLC? So if you have a hidden dangerous fault, it could be present such that your safety function will fail. So your fault tolerance becomes 0, and it's not acceptable for SIL 2 or 3 applications. So fail-safe design means that any detected fault will lead to a shutdown of the unit, and then the plant or machine will stop. So the availability for production suffer, the nuisance tip rate increase, and the availability is likely to be a lot worse than experienced with a standard PLC. So there's an example of dual redundant safety channel PLC architecture with diagnostics. So there's our input circuits, the diagnostic system, protection system, and again you can see the 4 switches. So both channels must operate to trip the output. So it reverts to one OOD if the module fault is detected, and diagnostics must check the other CPU. Common cause potentials in redundant PLCs. So if your design has got identical hardware and software, there may just be a possibility that both channels could suffer the same dangerous fault, and therefore both could be wrong. So some manufacturers deal with this problem by installing non-identical PLC processors with different operating systems. Others arrange for the PLC to operate in a non-identical modes so that the programs cannot suffer the same defect at the same time. Here's triple monitor systems. Principle 2 out of 3 is used in some of the most demanding safety areas, like your offshore oil and gas in the nuclear field. So these are based directly on design originally developed by NASA for your space flight control systems. So that's 2003 voters at each state. So to make sure that you have 2 out of the 3 still operational. Then if you look at application software for your safety PLCs, so with the safety PLCs, they're provided with limited variability languages, which in practice means high-level application languages, like your statement, list, ladder logic, and pre-written function blocks. Now, the function block approach provides pre-written and thoroughly tested modules of software called function blocks. And the user is left to assign names, channel addresses, times, etc. to customize the standard actions of the selected function block. Now the logic of the safety function is usually generated by using graphical tools the same way as with a standard PLC. Safety PLC feature a specialist compilation technique where your user program is compiled into machine code and then reverse compiled to compare with the original source code. So this technique is very helpful for executing changes to the application because it allows small changes to be thoroughly checked for the impact on any other part of the program. Failures in software do not occur randomly. Software does not wear out. All software failures are designed into the system. So when that certain combination of inputs, timing, or data presents the right condition to the system, it will fail every time. So for that reason, failures in software systems are known as systematic failures. So to make certain the software is performing as intended, the software must check itself to make sure it has done what it thinks it must done. Now, software diagnostics are programmed into embedded code. So one of the most effective software diagnostics is flow control. And here we have a picture of program flow control. And program flow checking makes sure your essential functions execute in the correct sequence. At key points in the program, the flag is set. So there's set flag 1, timestamp 1, set flag 2. And so at the end of each program scan, the flags are checked. So if there's any of the flags not that didn't realize, then that will give you indication you've got a problem. Now, the data used in safety PLCs must be protected from corruption. So critical data is identified by analyzing the execution flow or critical software functions. So that's often done with data flow diagrams, because this analysis identifies the software processes that perform critical functions that we found in safety requirements. And these functions include both the diagnostics and execution of the user's safety program. And the data associated with these software processes is termed critical data. And critical data must be stored so it can't become corrupted in an undetected manner by systematic software fault or by hardware failure. Now, here's an example of a data flow diagram with a chain of processes and a reverse calculation check on critical data. So here you can see process 8 provides the cross-check on process 1, 2, and 3 in the normal process chain. While processes 1 to 3 may provide a high accuracy result based on product specification, your process 8 provides a comparison of that result with the product safety accuracy, which is usually less accurate, but it will detect any erroneous software condition. Then firewalls around critical functions. So when your safety critical functions must be combined with non-safety critical functions, the design must include sufficient safeguards for non-interference. And that means any non-safety operations such as data acquisition from the safety system to a plant manager console screen can't hamper or inhibit in any way the safe operation or the fault detection mechanisms of your safety system. So if any non-safety function has the possibility of writing data to a safety system, the writes must be under controlled circumstances in an allowed configuration mode. So your system design must reject any unexpected changes to the system. And that is the end of this pre-recording for week 11.